Okay, so we are starting into the Laplace Transform. This is Chapter 6. We're not doing Chapter 5, the nonlinear systems of equations. Mostly, I guess partly because of time, but mostly as I look at our text coverage of that topic, it uses a lot of multivariate calculus and a lot of linear algebra, and since those are not prerequisites for our course, I don't see doing that. And so the Laplace transform is simply a transform. That is something we do a lot in math. And before I actually give the definition of the Laplace transform, let's look at what we want to do. Okay, so we have the statement of some problem. Okay, so here's our problem. It's right there. And what we would like to do is we would like to get over here to our solution. Okay, so there's our solution. Unfortunately, we don't know how in many cases. And so we're stuck. Okay. However, if what we do, and this is a very, very typical thing in mathematics, is this idea of a transform, and in particular, we're going to see it's an integral transform, and those are also very popular in math. What we do instead is we go in a roundabout fashion, and so I'm going to come down here using a transform. Okay, and again, this is just the general idea of how we tend to use transforms. So I'm going to transform the problem into, I'm just going to write P for my problem, like P prime or P star. How about we go with P star so we don't start thinking a derivative. And then that P star problem happens to be one that I know how to solve, or at least I stand a better chance of solving it. Okay, and so I get over here to an S star, and I get that solution, but then I possibly, again, these are always, any steps in any of this four-sided figure I just made here may be easy, may be hard. You know, for instance, if the top up here is easy, well, then I don't need this stinking transform. But if it's hard, well, then I try the transform, and maybe each of those pieces is easy, but maybe they're not so easy. And so I transform, and then to get back to the solution we want, we do an inverse transform. And so that's the idea, is that we will start with some problem, we won't have a good answer for it, and so we transform that problem down this way. That will be our Laplace transform of the problem. We will solve that problem going this way, and then we'll have to go back to our solution. And actually, again, as things go, this turns out to really be mostly an exercise in algebra. There's a lot of algebraic work in doing all this, and so that's where we're going with this. Now the transform itself, our definition. So if I have any function f of t, so you know, given f of t, then my Laplace transform, which is usually some fancy script L of some kind, my Laplace transform of f, now it's going to be a function of t. I mean, sorry, not t. We already have a function of t. Function of s. And so here's my Laplace transform. and that is going to be some function of s. And the way we're going to make it, another notation for this is uppercase, if I had a lowercase f there, uppercase f here of s. So that's another notation. But all we do is we do an integral from 0 to infinity of e to the minus st f of t dt. And that is our Laplace transform. So we started with f of t. Now we just do this integration and notice, well, the t's will disappear because this is with respect to t. And so this is t equals 0 up to t goes to infinity. And so the t's will disappear in whatever our function is, but it will leave s. So s will still be there. And so an example, the first examples they give in the text. So for instance, if f of t is just equal to some constant k, then our L, script L there, of f of s is equal to the integral from 0 to infinity of e to the minus st times k dt. Well, k is a constant, and so that factors out front, and so I get k, and times then this integral of e to the minus st. Now I can do that with u substitution and so forth, right? I'll get e to the minus st over minus s is what will happen there, and that goes from 0 to infinity. And so this is equal to k times, and when I look at the limit as t goes to infinity, well, e to the negative s times infinity, that's 0. So I'll get a 0 from that one. And when I put 0 in for t, so now I have a minus, and then when I put 0 in for t, I'll get 1 and a minus s there, and so I get k over s. And that is the Laplace transform of a constant k is just k over s. So you see it's a function of s. And I'll do one more of their examples in the text. So suppose we have f of t equals e to the at, something like that. Well, then when I do my Laplace transform, again, you see this is just, we do some calculus at this point, but most of these things are in tables. So it's not like in practice I have to do these integrations all the time, so you tend to look these up in tables, and we'll soon see why it becomes an algebra problem. But here we are doing calculus, and so I have the integral from 0 to infinity, so we have our e to the minus st times e to the at dt. Well, I can simplify this a little bit and say that that's the integral from 0 to infinity of e to the, I'm going to write it as a minus s all times t dt, right? Because when I multiply these two things, I add their exponents, so I'll have an at and a minus st, factor out the t, so I have that. And so now, again, it's an integration by substitution, basically. You know, I have a constant out here, a minus s. So when I integrate, I will get that e to the a minus s times t, all divided by a minus s. And so when I do that, then I have to do my limits, 0 to infinity. And so that then, as we plug things in, again, when we put in infinity, notice here's something very important, is that this only makes sense if S is bigger than A, right? So look here, you've got A minus S. That needs to be negative in order for us to put infinity in for t and get a nice number. Okay, and so and so we're going to put this out here, I guess, that we need S to be bigger than A. So I'll put that over here. S is greater than A. But if that's the case, then we'll get 0 and minus 1, because when I put 0 in there, I'll get 1. So 1 over A minus S. And so taking care of the negatives, I get 1 over S minus A. And we need S to be greater than A for this to make any sense. Okay, so that would be the domain of our S at that point. Okay, so there's our definition with a couple of examples. Again, we go back here and we look at, this is the big idea we will be doing. So we'll come back to that in more videos, but there's our video introducing the Laplace transform, so we'll stop it there.